Now, with the new camshafts and the control that we have, it has changed the way we port cylinder heads. The air speeds, the harmonics have changed. Everything changed with that smooth draw, getting that signal that before brutalizing, I think some of the fact we were having to use the bowls and the port volumes and the lower gas speeds that we were is because we had whole valve bounce. We were slamming the valves to the seat and just bouncing and bleeding cylinder pressure up the runner. And it was almost like a buffer, I think, more than anything. But that's all gone. And now we can go with ports that are more Formula One-like, what we call a high Mach Index port.
What do you mean by that, high Mach Formula One? I'm not familiar with that.
If you have a port that has to come in and bend, okay, and before, you had your carb venturi, and you had to get that runner as close underneath there as you could. And then the engine speeds went up, the runners got shorter, went away from there. You can't use the inertia coming out of the barrel to feed the runner as much anymore. And the bend in the runner with the engine speeds going up had to come out. We've known for a long time that the height of the short side relative to the valve diameter is critical to engine speed. If the short side's too high, it doesn't matter how big you make the bowl, it's not going to RPM. It has to be a certain height, and that height is between 50 and 70% of the valve diameter, somewhere. And once you get over 70, all bets are off, it's over, forget it. That engine will not RPM because the localized airspeed goes to the Mach limit before anything else, and it forms a choke. But that's what turns the fuel. That depression at that short side apex is what grabs the fuel and puts it in the cylinder. So you have to have an airspeed, and if it's too low, you can't control it. You got fuel fallout, splashing on the back, the wet flow's horrible. So that's why, some head porters say I'm a short side freak. Well, yeah, I understand. It's absolutely finite, the layback, the apex, the airspeed. And we know that the airspeed shouldn't exceed the test pressure. It shouldn't exceed 360, 380 feet per second average across it. But we also have to put up with, like I said, port offset relative to the valve guide center line. And as you move that port away from that guide, your velocity gradient downstream increases. So your flow separation increases. Your coefficient of discharge drops, and it's harder and harder to extract the potential that valve could give you. So now, when I was working on the DRC E3 projects with Tony McAfee and Richard Maskin, we had a cylinder head, and I do intake, exhaust port, combustion chamber, and send him his head, and he'd send me his version. And we would make changes and look at each other, what each were doing, and it ended up, he used my exhaust port chamber and his intake port, and he told me, he's like, man, we're finding the bowl volumes are shrinking, the short side relative to the valve diameter is shrinking, the layback's increasing. He says, these things are going like F1 stuff. It's line of sight. See as much of the valve as you can and still turn the fuel. That's where we're at. He told me, but I didn't listen. I was too stuck in my ways. 5 years later, I understood. When I did the JC51, and the JC51 still has like a hybrid port in it. It's still a little big on the bowl and a little high on the short side. But it kind of fell into our lap because he doesn't have to wind it up to 11 with a single carburetor. High Mach Index ports. What is a high Mach Index port? A low Mach Index port is a port that has to make area changes rapidly and has high flow separation. Okay, increased turbulence, lower coefficient of discharge. Its effective flow area is very high. So what happens is you can't utilize, if that valve's potential flow gives you 2,000 horsepower, you can barely get 1,500 out of it because of the energy lost through the system. So you see here, this is like a runner on a 23-degree small block Chevy. You see the dead zone on the roof, dead zone here, and dead zone here. When you have a port that's real low and offset to the valve guide center line, this area right through here is still the same, You've just got to move the port over. So you get instant flow separation, and you're doing everything you can to get the air over there, and the air will not go over there because the air is like electricity. It chooses the straightest, easiest path. That is bore center. If you want to know where the highest air speeds in your induction system are, you take a string to bore center, you lift it as high as you can, and it will be bore center, the right side of the short side, and the roof. Straight line. So no matter where you put that port, bore center. My job is to accent the natural flow path as much as I can to bore center. Try to get that airflow without air separation, turbulence, with the highest discharge coefficient, meaning the highest flow per unit area. Smaller port, same flow, utilizing all the area, instead of having to make it huge with a lot of flow separation flowing that amount of air. And it's going to kind of extremes on some heads. Now this is more that a really like a modern pro stock or comp head. The short side, can you see my cursor here? This short side layback angle right here is more. The short side is lower. It's more, you can see 85% of the valve looking down the runner itself. If you look just right down the runner, you can see 85% of the valve. And the old heads, you might see 45, 50%. But we still build enough airspeed right here at that short turn to turn the fuel. And on the wet flow bench, I was the first one to take some pictures of the wet flow and the separation and the vortex generation within the combustion chamber and plot that relative to some of this short side airspeed. And then I had a cylinder head made out of clear acrylic with strobes and ultraviolet light. So we used a dye that fluoresced at 420 nanometers, and making a strobe out of ultraviolet is almost impossible, I learned. So I could see the fuel droplets going through the runner. And if you got the short side airspeed just right, that fuel droplet goes in, and when it sees that low pressure area, boom, straight down, 90 degrees. It will yank it off the roof and send it down into the cylinder. If that short side speed is too slow, boom, runs into the back, deatomizes, streams of fuel, makes the engine detonation sensitive, because now you have fuel fallout, which makes the lean areas even leaner. Bang. As a matter of fact, the quickest way I know, I did a test one time on a Pro Stock engine. I polished the runner to a mirror just to see what it did. It didn't even come off a peak torque before it blew the rings out of it. There was so much flow separation. The walls just grabbed the fuel. It leaned out and bang, lifted the ringland instantly. Where did I learn all this? This is who I learned a lot of this from. These engineers did the same thing we're doing right now, no different. They just didn't have the metallurgy, the processes, the alloys, the backing, the machine capabilities, or anything that we have. You know, back in the 1930s, they were able to make 3,000 horsepower. Now, these guys, we make power for fun because we like it. They did it to save our lives and our way of life. I mean, talk about a motivation. More R&D, research and development, has been done into metallurgy and engine design, auto cycle 4-valve engines from 1930 to 1968 than since that point. Now, if you don't study history, you're doomed to repeat it. A lot of the R&D techniques and stuff that we use, I'll show you here later, is developed by these guys. You know, if you study their R&D process, you study the Rolls-Royce. Okay, let's look at this. The Napier sleeve valve engine, one of the most powerful engines, other than the Rolls-Royce Cressy, if you want to look that one up, but never went into production, was a sleeve valve engine. Do you guys know what a sleeve valve engine is? There are two sleeves. The piston runs in one, and the outer sleeve rotates. So you're opening ports as the pistons rise and fall. So it gave you instant, huge amounts of area. Just boom, instantly. So they didn't have poppet valves, no Valvetrain, no nothing. And those things made a lot of power, but they couldn't make them live. There was no metallurgy, heat treating processes, and alloys available to make the sleeves compatible with each other so that they would work. They spent $1.2 million in 1942 to try to develop the alloys in those sleeves. That's $22 million today. And they didn't even get it working until the end of the war. ProStack technology in engine development is working with the manufacturers to develop the components and the processes and the machining to let us to move forward. That's what it is. You know, I hear ProStack technology all the time, and all that is just slowly developing things. And that's why it trickles down into the aftermarket, you know, all these processes, compacted graphite blocks, all that stuff. They knew what I'm about to talk about 80 years ago. Mean gas velocity, the mean gas speed in the intake tract. As the piston speeds increase, relatively, proportionally, the mean gas velocity has to go up. And notice I didn't say engine speed here. So the mean gas velocity is the piston speed, piston speed port area ratio. It's not really difficult. And the idea is to shove those gas speeds as high as you can. You can't shove them as high as you can unless you have an efficient intake port with a high discharge coefficient. If it's a crappy big intake port, the mean gas velocity is going to be low. If it's a port with localized velocity shock or something like that, it's not going to be able to capitalize on it. It's going to choke off before it even gets there. So my job is to design this. Now, this is, what is this, 1910. He's sitting here talking about piston speed relative to engine speed and how much the mean gas velocity is in the runner. They knew this. It's the same thing I'm using now. It's just you notice their piston speed's 3,000 feet per minute. Well, they didn't have rods strong enough or pistons strong enough or blocks strong enough to start shoving the engine speeds higher than that. So for longevity, they had to make 2,000 horsepower for hours and days on end at constant throttle. That many BTUs, that much energy, getting rid of that, being able to handle that, being able to make that live, that's an engineering marvel. It really is, especially with what they had to work with. So this is the piston speeds in modern engines. Now, engine speed and piston speed are not independent of each other. They are related through the bore-stroke ratio and everything else. But the mean gas speed of the intake runner is relative to the piston speed more so than the engine speed. You can have a high engine speed and a low piston speed. And vice versa. You can have a low engine speed and a super high piston speed under square over square engines. Small bore, long stroke, the mean gas velocity, you can't handle it because you have too small a bore to get enough valve area in the damn thing to feed it. Well, hyper over square engine is an F1. And we know from endurance, an endurance engine cannot exceed 5,000 feet per minute. With modern technology and some of the processes, yeah, you can get it to 53, maybe 54, make it live 24 hours in a race. But that takes an engineering, that takes a lot of engineering to do that. So even though those F1 engines are turning 20,000 RPM, their piston speeds are 5,000. Now, an extreme, down here at the bottom, an extreme IHRA Pro Stock is an under square engine. We're talking 25 bore, 650, 6.5 inch strokes, you know. Their piston speeds are higher than they ever dreamed were possible. So as your piston speeds increase, your engine durability drops relatively quickly, real fast. Point in case, we were doing 632s, 648s for bracket engines, and those guys have to run those engines 300 runs, so 7,500 RPM. Piston speeds, engine speeds, everything we built the engine around would last. They'd go out. Scotty Richardson put 450 runs on an engine. It came back 70 horsepower down. Tired, worn out, but not broken. Then they came out with Top Sportsman, and these guys are turning 85, 8,800. So we took the same engine, cammed it up, gave it more area, and did that. Now, it would last 100 runs if you're lucky. If you're lucky. Just that jump in piston speed decreased the engine's lifespan by a factor of 10. And like I said, they plotted all this. All this is out there. they plotted the mean gas velocity of all these Grand Prix engines, 4-valve, 2-valve, every engine out there. Now you see here down here it says tortuous inlet. Proper English uses strange terminology. Tortuous means a lot of turbulence. Their coefficient of discharge is low. Like a single 4-barrel with runners that come out all the way around the harmonics gone completely out of sync. It's just not a tuned system. So of course their mean gas velocities had to be larger. Like if you take a 23-degree or a conventional big block Chevy head, take a 20-degree cylinder head. The port volumes in those have to be huge in order to run. Their mean gas velocity is 20 meters per second slower just to navigate the air coming off the wall and going inefficient. So if you have flow separation, you have to make that area bigger in order to get the same amount of flow. There's just no way around it. So that lowers your mean gas speed. So that causes you to do other things in the system, which is plenum and carbs and everything else, trying to get the average airspeed back up to fill the cylinder at a higher VE. But as you notice, as they started with the 2-valve and the 4-valve, higher bore stroke ratios, the mean gas speed got shoved up. And we're still there today. That's where we are, 70, 80. That's because if you shove the mean gas velocity too high, you get into the choke. 0.55, 690 feet per second. What is a choke? A choke is, once the airspeed reaches that point, let me back up. What I want to do is when that piston drops, it's going to hand me so much energy. I want to use that energy to accelerate that air in that runner as fast as I can to a certain level. Once it reaches the choke point, the efficiency falls off because the inertia increases to the square of the velocity. So if I could double it, the inertia goes up by a factor of 4. So if I could double it again, that's 16, see? But, so I want the airspeed. I want as much airspeed in there. I want to turn that airspeed into boost. When that valve's closing, that air is still ramming in. That's how come we get 124% VE in an NA engine. Valve closing, it raises the pressure. You're exchanging velocity for pressure. But at a certain point, the energy that it takes to accelerate that air faster, you don't get a return in cylinder fill. All you're doing is stretching the molecules out. Take a syringe sometime and just pull the plunger back real fast. It's going to snap back. You hit the mean Mach number of the tip. Take the tip off. Do it again. You can get more air in there, but you're still choked. You're just stretching the molecules out and getting nothing in return. So you want to shove the mean gas velocity as high as you can. Bore stroke ratio. You can't have valve area. You can't flow air unless you got valve area. You can't have valve area without a big bore. So the whole NA racing engine is very simple. It is the biggest bore, shortest stroke you could possibly design into a crankcase. And of course there's limits to everything. Once you get over about 600 inches, there's no bore space available or 700 inches, there's no bore space that's really going to allow you the proper bore stroke ratio, over square ratio. And once you get below 350 cubic inches, it's very easy to have too big a bore, short a stroke. And on like a 265, we had a 302 engine, and its shift point was about 11.2. And we had a 185 bore. We ended up with a 4060 bore because I could fit way more valve area in that thing than it needed. I could fit way more valve. So why am I have this big bore short stroke and the piston speeds were too low to get the mean gas velocity high? It was going through the traps at 5,400 feet per minute. If you look at all NA engines, they go through the traps at 6,000, 6,500 feet per minute mean piston speed. They all do that because that's the most efficient range to get the mean gas velocity up to 70 to 80. That's why they do it. So if you go too high over square and you got too much valve and too low a piston speed, there ain't no way to get there. So you shrink the bore up, increase the stroke, shrink the valve up, and get it right in that sweet spot, and boom, set the world record second pass. Now, this is the intake valve area to piston area ratio. And as you can see through history, once they understood the over square ratio and where to hit these things, they all end up right about there. And a 2-valve, some of these are 4-valve, by the way, in the later. You see that's up to like 0.35, and a 2-valve, The best I've seen is like 0.285, 0.29. Intended purpose dictates design. So now let's get into high Mach inlet ports. What kind of classes utilize a high Mach index port? F1, Pro Stock, Comp Eliminator, and Super Stock. And I tell people Super Stock, and they look at me strange, and I'm like, it's valve limited, its gas speed is through the roof, and it has no area to work with. So all you can do is drop the short side and aim everything right across the valve. But you still have to get airflow. That's the trick. Airflow is proportional to power. You're not going to make power without the required airflow. If you flow 400 CFM, you can make 900 horsepower if you can design everything to extract it. So with their airflow, I still have to get the airflow up in order to make the power, but I have to make a high Mach index port because I'm valve limited and port limited, severely port limited. So I have to use that area at maximum efficiency to accelerate the air without nosing over. A high Mach inlet port, all that is, all ports will nose over after the choke point. A high Mach index port noses over a little less. It just allows you to capitalize on the airspeed upstairs a little more. Now, how much power is that worth? 30, 40 in some cases, depending on where you start. Sometimes it's not that that cylinder head is that good, it's just that the old cylinder heads were that bad, you know? It's like the Formula One air race champion at Reno. He brought me the engines years ago, and I looked at it. It's a little teeny Cessna 150 engine. I'm like, you got to use stock pistons, stock rings, stock everything, stock cam. They measure the cam every 20 degrees. You can't cheat on the cam. You can't cheat on anything. But welding and porting is legal. So I took the plenum, you got one single carburetor coming in the bottom, and these runners coming directly out of this, no plenum volume. So I welded the whole thing up and made it nice and swoop and got a little plenum volume in there. And then I had a 1.5 inch tube. That's my choke. So then I just gauged everything off of that. And in a stock engine, 2800, that's about it, RPM-wise. And they got him to 4,200 with a two-blade. And then after I was done, he was 4,800 with a three-blade. And he passed them like they were standing still. It's been known for many decades that the localized airspeed at the short side apex can limit engine speed. I already hit on that a little bit. No matter how much CFM it flows. There's the Brodix heads, spread port heads were designed in 89, 90. And it was the old way of doing things. Come straight in to an apex, then lay your thing back, lay your short side back, and that layback controlled the engine speed, where it would choke off. So if you wanted it to wind it up, you'd start laying it back until the RPMs would come up. They had a low mean gas velocity. They were huge bowls. They came straight in, straight down. Big, huge bowls. Well, they had to have huge bowls because the short side apex speed was so high. So then later on, we started designing them a little more swoopy, a little more aerodynamic coming in, concentrating on the air speeds and making the airspeed the signal right in the center of the port as much as we could, where those were just like a straight line. And we had total control at that point. Those heads will nose over at 7,800 no matter how big the bowl is because of that short side height. The height, and you can't lower it because there's no, you'll go into the water jacket and what have you. So when Dart did the 18 degrees and then the 14 degrees, they allowed that. You can see it in the short side in the water jacket itself. The whole water jacket is laid back. It's not square underneath there. It allows you a lot of latitude in that area. This port right here has what we call a hypercritical short turn. It's called an LS7 head. Now, why would you do this? You know that a super high, and this is 75% of the valve diameter. Nothing, you would never do that in a racing engine. It would nose over like crazy. So why would you do that on purpose? Well, engineers have to work in a box. I don't. They had to fit those manifolds under a Corvette hood. It was that high above the valve covers. So they had to come out of the thing, come all the way around into a plenum to get the rudder length to harmonically tune the system at the lower RPMs. And they have a broad power band. They have to operate going down the highway at 1800 RPM, just chugging down. And when they hit the throttle, they have to have signal to move fuel into the engine. It's like high and low pressure systems. Everything moves from high to low. You have to build a low pressure system down here at the venturi and the valve to move that air to get the signals to start moving into the cylinder. They also have a 2200 intake valve, which is more valve area than you would ever use at 15, 18, 22, 25, or even 3000 RPM. So how are you going to manage that much valve area and that much runner volume at 1500 and make it fuel efficient and pass EPA standards? You build the airspeed at the peak of the apex of the short turn. That airspeed right there, when you hit the throttle, that's the pressure drop that moves the air into the cylinder. What happens when you take an LS7 and you radius that off? You pick up flow, and everything below 4,500 is dead. You kill all of the torque below 4,000. That's why. You have all this valve area, and your mean gas velocity is so low, you can't move air into the cylinder, because now you don't have a pressure drop. And this is a model of an SB2 heads that I used to do for DEI. And yes, my heads were on the car when Earnhardt Jr. won his first race at Dallas. They invited me to the race and let me watch. That was the first NASCAR race I ever went to. As you can see here, the boundary layer separation in this one happens at the apex. It achieves flow separation even before the apex of the short turn. And look at this. You see this flow separation here? This is your flow zone right here. It shuts that flow zone down and makes it smaller. And the apex, this is a tuned port for a given RPM range, and all the flow separation is right there at the apex of the throat. And your flow zone is much, much bigger. So what the point I'm trying to make here, intended purpose dictates the design of the port. You can't use a high Mach Index port in a low-speed engine, like you can't use an LS7 in a high-speed engine. You know what? When I worked with GM on their IRL project and a couple of the other projects with 4-valve stuff, that was quite an education, because at that time they were starting to flow at higher and higher test pressures, because they noticed if you look at the calculations on any flow bench, if you double the test pressure, you can easily use the square root of the difference of those two pressures to find the increase or decrease in velocity. But it's not relative after a certain point. And what they found is the ports that they were designing for these engines were going hypercritical, like an LS7 apex, at 65 inches. And by 110 inches of test pressure, the whole port changed. Everything changed. And everything changed. If you look at a new Suzuki, Yamaha cylinder head, single cylinder, they all have the port I'm about to show you. It's not only high Mach Index, it's offset, which is hard to grasp. The throat itself is not concentric to the valve guide. It's moved back towards the short side. So on the back wall, you have 7/8 angles, and the short side goes right to the seat. So what happens to your seat register? When you move that back, there's nothing to hold the seat in. So even on IHRA Pro Stock heads, Extreme Pro Stock heads, those are high Mach ports. We move the whole seat ring back 100. We offset the seat ring back towards the short side to give enough register to hold it in the head. Because once you lay that back, you just destroy all that seat ring caves into the cylinder head. I tried that on the Pro Mod, but that was a dumb move, because you have to have repairability in those heads because they blow up all the time. And you can't sit there on the mill and dial everything in and offset. It was a pain in the butt. You got to be able to pop them, weld them, remachine, and go. So this is an early Cosworth head. I think even 68, 70 is what they used this cylinder head. And this is the difference between a modern high Mach port and an F1 or IRL head considered what they did before. And what I did was I had a little twist on them. I actually took the short side and made it a little wider. So it came in, the roof is still round, and I'll hit on that here when I show the ports. So basically, you've got the seat, 60, 70, 75, 85, and a 90, or whatever angles here. You've got like 6 or 7 angles from the seat, a nice, beautiful turn, and then this goes right to the seat. You've got this, and then the seat's right there. Because there's no flow there anyway. The cylinder wall is right here. So, like on a Hemi, why does a Hemi move so much dang air? You have a valve like this, and excuse my artistry, and you have a combustion chamber like this, and you have the cylinder wall right there. So when that valve opens, it has absolutely perfect pressure recovery right down the cylinder wall and right into here. So you don't need any seat there at all, any angles there at all. On super stock Hemis, those things will move 480 CFM of air through a 2250 at gas velocities that are stupid high. And that short side comes right to the seat and down the bore wall. The bore wall is the extension of the port. And that's why its pressure recovery is so good. They actually have a discharge coefficient that's Hemi related. The Hemi is the best flowing cylinder head ever devised by man. So if that's 100%, you can rate every other port off of that. You don't have to use or there's a straight pipe coefficient and a valve. There's so many. I use the flow bench. The flow bench is my testing instrument. That discharge coefficient for that orifice in that bench is 146 CFM per square inch of valve area. So if I have a certain size valve or cross-sectional area, I will rate it off of that. And that's my coefficient. So modern ports based off of that are 92.5% efficient. And I saw a cylinder head that Jason Line did. It was 93.5. I've never seen that in my life on a pro stock head. 93.5. So if you get a cylinder head like that, do you think you're going to go in there and pick it up? There's only one way to go from there, and that's backwards. You don't touch it. You don't breathe on it. You don't do a valve job on it. We always say if you look at it wrong, it'll kill 10 horsepower. So I had a customer that came to me, and he's doing this engine now. I'll show you the port molds for it. And it wasn't a true high Mach Index port because there was a lot of port offset relative to the valve guide center line. So there was flow separation. I had to make allowances. So this is the way I look at it. I needed a 2325 valve to move 500 CFM, and I calculate the power potential at 87% of the gross lift of the valve, which is 0.42 to 0.43 lift to diameter ratio. So you can tell what the maximum lift on your cam is pretty easily. If you have a 2200 valve times 0.43, that's going to be about as high as you're going to lift that valve and dynamically control everything. 87% of that is the true power potential that you can extract from it. Because minus lash, deflection, and everything else, that's going to be about where the valve's going to end up. So, the port length is 6,850, and I have a runner length of 2,250. That's my runner. Because this thing has to make peak torque at 96 and peak power at 11.1. And we did a couple of these engines at Rares. And the required CFM is 480. So I know I move 500 CFM. My gross lift is 1. So at 87%, I've got 485. So I should be able to make the power required out of this, which is close to 1,200, or 11 something. Now, 9,100 total intake track length. The whole intake is 9.1, and the port is 6,850. So here's the port. Well, this is a side view. As you can see, it's nice. It's almost parallel, these lines. But you also see all the angles here. There's nothing here. So everything is, the throat, concentricity, everything is moved back and laid back to try to get as straight a shot and capitalize on the area as much as possible. Now, as you see, the push rod is right there. And you see that flare. That's because most of the runner is in the head, because they only have that much sticking out. So I have to continue that taper into that push rod area and then open it up. Now, everything throughout that port has to be a given size. And the taper has to be a certain angle, certain volumetric increase, and a certain airspeed drop or acceleration to that point. And I can't mess with that too much. So I also have to maintain a cylinder to port volume ratio. So let me run you through that one. The cylinder holds so much volume, I got to have that in the intake tract. You almost can't get there, but you also want to capitalize on the first harmonic, the earliest harmonic, the most powerful one. So you need to have your runner this long, because if you go to the next harmonic, the pulse strength drops, your VE drops. So you want to have that first one. But now you have to raise the RPM, and it has to get shorter. How are you going to get the volume out of it? That's where taper comes from. That's why we taper runners. It's volume increase. We're trying to gain volume without slowing it down so much that we're dissipating the pulse's energy. And that's why you see the more taper you have, the tighter those radiuses get. I say with a 0 taper, you can have a 1-inch radius. And with 30% taper, you should have about a 1/2 inch. And then with 40% taper, it should go down to about 3/8. And with 50, it'll go down to 1/4. And people make the mistake of trying to put those small radiuses on less taper, and it just shears and chokes the top off. So the amount of radius is relative to the taper, and the amount of taper is relative to the amount of volume that you need in that runner relative to the volume ratio of one cylinder. And the shorter it gets, the harder it gets to get there. So what happens if you could only get 90% in that runner? The whole intake tract. The 10%'s got to come from the plenum, so it's got to be bigger, which can make it lazy down low. See what happens? Give and take, give and take, give and take. You notice how wide the short side is. NASA knew for a long time the most aerodynamic shape to turn air around a corner without increasing cross-sectional area is that. Because a square area, let me erase this here.
Got the eraser right there.
A square area does not utilize all the area when it tries to turn around a corner. If you have a square area right here, your vortex generation here, the air does this, compacting the airspeed at the short turn. So, make it like this. There you go. Each corner of that short turn has vortex generation that shuts that thing down. This, in all high-speed ports, I utilize that, and I will show you that in this port. All of my ports, and even on a 23-degree small block Chevy, you'll have the common wall, the short side, and I'll do this. Because I don't want a separation, flow separation. I don't want that volume over there. It hurts me. But I got to turn it somewhat efficiently, and you can turn it a little bit efficiently by canting that wall over and getting your roof airspeed up. What you're trying to do here is you're trying to get the roof and the floor the same airspeed. Of course, you can't get there. You'll never get there. The whole idea is to get it as close as possible. So you have this. This is looking on the port. Look at the vena contracta here at that port. It's highly pronounced and deep in the port. The reason for that is you're using 55, 58 degree seats. You're cutting those angles at 10 degree or less. And why do we do that? If you have a 45 degree seat, the apex of that throat is 260 thousandths below the seat. You're forcing the air to set up for the turn around the valve. But when you put a steeper seat on there and use those angles, it moves it down. You can use a bigger area at the throat and still be able to set the air up for the turn. So the throat's apex has to move deeper in the bowl the steeper that seat gets to give it time to set up for the turn around the valve. And the roof is real radius, small. And my roof airspeed is controlled by that and the wing in the middle. The wing is a structural support for not only the spring pad, but the guide itself. So you have to have that in there. You also notice that over here, the area is far less than bore center. Because as the air goes around the push rod, it doesn't want to go over there. So don't give it any area, speed it up. And all you're trying to do is getting your velocity gradients out of the port so you don't have flow separation. That's it.
Just back to something you were touching on, obviously the short side. So one of the biggest questions I get being here in Rottler and the porting machines and people, this conversation of dimpling and whatnot goes on. Now, my kind of opinion on it personally would be that, I think if you anything in airflow and with a little, I know you kind of do the same thing all the way through, you probably don't get the good result. So it's that kind of what you just ended on is you're never going to be able to get things to be the same, which is what you want them, so you have to do manipulations. What's your take on, if you're doing dimpling or anything like that, is there any benefit to just, I call it selective dimpling maybe, or just maybe in one little area? Is there any?
I guess first we have to understand what we're trying to accomplish. And if you don't know the problem and you just put something in there because you think there's a problem, that's no good. If you utilize something, design aspect or something you're doing because somebody told you it worked, that's not a good idea. To me, dimpling is a gimmick, but it can be a fix for a port with too slow airspeed and too much fuel fallout. If you design your port product properly, you don't need that. That's my outlook.
And in that, do you see it, I know some people have played around with it. So would you say, I guess, I don't know if you've seen it at all, but just if you were going to do it, just doing one area or anything, just because of the boundary layer condition, you may get that, or what's your opinion?
On the wet flow bench, you can see exactly what happens. In the low speed areas, the fuel will fall out, especially on the floor. It forms trails in any low speed area. The wall will carry the trails. The floor, there's huge trails, which is why in some of my ports you'll see a wing in the middle of the port. And all that is a high velocity spike that takes those trails, compacts them, and spits them into the combustion chamber. It's about 4.5, 5 foot-pounds of torque. It's not there to make it move more air. It's not there to solve a problem. All it is a velocity spike to pick that crap up off and spit it back in the airstream. But when you design a port with a wing in it, it has to be designed around the fact the wing is there. So your flow has to get wider to make up for that area. So you can't just put that in there and have it work, like dimples. If the port's designed properly, you won't need them. But let's say 4-valve stuff, a lot of that, the port is as 2 into 1. So you have this low-speed region in there that's real lazy. Sometimes that will help in those areas.
Okay.
And me, I'll just grab like a 36 or 40 grit finish and just make it rougher than a cob and race it.
Increase a little bit of turbulence for more airspeed.
Just jack the boundary layer off so you don't get as much flow separation.
And that was, these, I've never seen this before, and I like, the shapes. And
I have the NASA tech brief. It's on my website. NASA knew this in 1968. They were trying to turn air into F-111 single engine, and they got buffeting because the area increased. At certain engine speeds, they'd pull back and flame out the engine. You ever heard of the flame out? That was the flame out problem. It was a big area. You'd have this high-speed air and this big and accelerating again, and at certain engine speeds, it would set up a harmonic there and just put the flame out. So they had to develop a way to turn the air efficiently into the engine, and that's what they came up with.
And with the, vortices, sometimes good, sometimes you want them, sometimes you don't. Is there anything that you've seen in porting where you're looking to control that and add it in, or kind of you were talking about 4 valves?
I want turbulence. I want all I can get in the chamber. I want to save it all and dump it in there. The wet flow picture that has been around forever. I did it in like 2000, I think. That's a combustion chamber in a pro stock cylinder head using ultraviolet, 50% water, 50% alcohol, specific gravity about 0.75, which kind of mimics fuel a little bit, and the fluorescent dye, and that's at like 48, 50 inches. But if you see here, this spark plug, it's wet on that side. Every time we pull the spark plugs out of the engine, there'd be black carbon right there. And it was like, we didn't know. See, that's why I said when I got this bench and I started doing this ultraviolet stuff, and I just got wet. I just stand right in front of the bore, the camera's in the corner, was zoomed in on it, and I would wear a raincoat and I had a blast shield behind me. And for months and months and months, I would go in, and I felt, it's like I said, it's like a blind man being given the gift of sight. What you see here is the exact burn on that piston when you look at it. So what I tell people is if you get a wet flow bench and you play with it for a year, you won't ever need it again. It teaches you to read the piston like a book. Everything that happens in that combustion chamber, the flow separation, the vortex generation, which I can show you here. I think, yeah, see this vortex right here on the wall? There's a vortex right here and one right here. And you notice there's nothing over here. Where does your piston always lift the ring land and detonate? Yep. There's no fuel over there. It's not fuel wash. People look at combustion chambers and it's clean on one side and you call that fuel wash. No, that's fuel isn't, because there isn't any there. It's like frying bacon in a pan. Wherever the most grease is, that's where it's going to be dark. And this is fixed. This is a combustion chamber modifications, bringing the exhaust side in to move the vortex off of the plug. It compacted it, making this sharp. These are vaporization regions, and you can see the vaporization ridges of the seats. Those angles in that port, those are vaporization ridges for that fuel. They spray off of those. And if you radius that seat, that engine, never run a radius seat on intake. And you notice there's nothing hanging out over here on this side. That's because we put the 5-degree quench cut, the soft chamber in there. That's what that does. It takes that vortex and moves it in. So wet flow on a hull wall. You don't want a slow area. And that's why I say I work to try to get the velocity gradients out of the port, try to get the air speeds as even as I can, because any dead area, the fuel's going to fall out of suspension. And in high-speed engines, that droplet size, you see Warren Johnson, all these guys in the carburetors, they're over there changing their air bleeds. They're not changing fuel flow, they're changing droplet size relative to the atmospheric conditions. If it gets hot, they need a bigger droplet size. Otherwise, it takes up all the oxygen and the engine's VE drops. That's what they're controlling. So if you have deatomization on a wall, the droplet size goes to a solid stream. That solid stream of fuel won't burn. It burns too late to create usable cylinder pressure. It just raises your EGTs and burns the exhaust valves up if it's too bad. So I would make it dimples. You could do that. I would rather just move the wall up and get the airspeed up.
Yeah, sure. No, I like the way you put that. I mean, and there's a lot of things in. Oh man, I look in machining and seat cutting all the time and stuff, and we see this so many times around different applications of you can always find workarounds or ways to cover, I guess, inefficiencies or inefficient designs. Right?
It's not the machine, it's the machinist. Mm-hmm. I mean, I've worked on every single seat and guide machine you could put, even old Oben tarps or tarp or whatever they were. Stones. When I started as a kid, I had a wet grinder, which was a Cadillac of a machine back then. You had dry stones and you had a wet grinder, man. The wet grinder was awesome. I would be at that thing. It'd take me 12 hours to do a valve job, And then we had the single point cutters, the Myra cutters is what they were. And they were weak, suck things. They couldn't bite. You couldn't take any material. They'd bend. They were real weak. And then we had the single point cutters. And that opened up a huge amount of doors. But every machine, no matter what it is, even if two different mills have different feels, different backlashes, different sets, and you just got to get to know that machine. Whether you're working on a SERDI or what have you, there are certain things that you learn with that machine to decrease or increase your concentricity and stuff like that. You know what I mean?
Sure. What in terms, you mentioned something there. I think that was critical. You were saying, we don't want to put a radius over here on the intake, and in terms of the manufacturing and the seat and guide machines you have today, and what's your take on the sharpness of the angles, and I guess the conversation of different. You started with grinding, then you have the form cutter stuff. Obviously, Nguyen and SERDI have single point machines now. Is there benefits, pluses, minus, things you like, don't like? What are you, when you're looking at this,
Well, there's a cost-benefit analysis there that you have to make. I mean, with the single-point contour machines, your accuracy is a magnitude better. You're going from 1/1000th to a tenth. The cost, however, is hard to justify for many shops. And the latitude of being able to design different seats, change those angles, the sharpness of those angles, as you hinted to, allows us to change things on the fly. Remember I said the steeper seats move the apex of the venturi down. What happens if you do a lot of valve jobs? Okay, well, on that you have to change those angles. So instead of a 65, you go with a 67 and cut it a little harder, just a little bit, to get that turn out the valve back that you had, which is why you don't do valve jobs on pro stock or comp heads, is if you could all help it. You don't want to sink that. That venturi relationship needs to maintain. And that gives us a lot of latitude. And it gives everybody a lot of latitude to design whatever seat angles fit their intended purpose. So that's why when I get a head from like Matt Bieneman or Carl Foltz or something, I say, no, send it back to them. I'm not touching it. Those heads are booby-trapped. They're taking right to the razor's edge and they're pushed about 1% past. If you even touch it wrong, boom, you kill 20 horse. I had that happen, the Raptor heads. I made the mistake of doing that at Rear Morrison with the Raptor heads and putting it right at 91.8% on the throat. Well, you do valve job and somebody go blend it, 30 horsepower, gone, just gone, once you destroy that relationship. So I just kept them small and killed about 20, but as it blended out, the power would actually go up instead of it going down. So a lot of these high-end heads that are designed for a specific purpose, I just say, yeah, just send it back to him. Otherwise, I'd have to take a mold of it with epoxy, slice that, put it on a shadow graph, document those changes, order a cutter. But those heads are, the contour machines are really good. We use them for a contract with a high horsepower engine contract with a company that we do a lot of those engines. They have to be exactly the same. They have to be on critical max, every one of them. So that's a good deal.
Yeah, I mean, I've always looked at it, for Rottler, we've discussed it and all that, and there certainly are wonderful machines that are out there. We only have form cutting tooling with our SG9s. And I've always had that, for that world, obviously, the method of cutting and for the prototyping, the development, you can't beat that.
I use a Rottler. I haven't even used it. I have never used a contour
Really?
in my life. No, I still use that. And custom cutters. And if I have a weird valve job, I have single cutters, single blades,
okay.
So I can come in and.
So then you'll just manipulate.
Yeah,
through there,
it takes 8 hours to do a valve job,
Yeah.
but you can hit every single angle.
Well, and I think it's, when you look at, there's always, you can go as fast as your pockets are deep, I suppose. It's kind of the same thing in machining. What do you need? What's your application? So I always look at it as the machine tool side, and you can still certainly get a lot. I like that method. I never thought about just doing single angle, and you can certainly do that quick. And for someone who wants to play around or do this stuff, but not at the price
absolutely.
point of a single point machine, that's a good way to do it. What's your take on
And sharpness. You hit on sharpness. of
sharpness
the
between the
angles.
angles? So with the form cutters, and I deal with that.
Yeah.
That is
You
a
can't
thing.
get them too sharp.
And we've had, Rottler, we work on that and have to track that because when you have a form cutting thing, you're a supplier, we have this large library.
Yep.
And that's the number one thing that I see in the manufacturing side from our customers.
It takes a concerted effort to do that.
Yeah, they're very,
And-
and it runs, and manufacturing, it happens.
Yeah.
To be honest, we do have them where a batch comes in and it's, the wheel didn't get dressed that day.
Mm-hmm.
That happens. But that's something that I've learned, and you have to control that and make sure that's right.
On the early form cutters, we used to have to go back in with stones and glide them and get those. Yeah.
And that was, people have had that, and I've even had discussions with your single angle stuff. For me, I bounce between the automotive world and then this diesel world. And in the diesel world, it's single angle, and for production runs, we're usually using CBN.
Yeah.
I've had that. What would be the take on that? I mean, have you experimented with that at all for doing that final cut, just maybe a single angle for the seed, or playing with one after you've maybe done a form cutter and using CBN even, or?
No, I've never used CBN. I've never used CBN. Getting those angles sharp, like I said, those are vaporization ridges. The fuel vaporizes off of those. Otherwise, it just goes into the thing wet. And it initiates, the air turns over those much more precise. And one of the major things, you can do for years, I was taught by the guy who was taught by Lee Shepard how to blend seats and how to do the Venturi and the Apex. So I still do it that way, but I'm having to get away from it because the sharpness of those angles and how that leads in can control the stability of the airflow in that port. And sharp edges will make it, like a SB2, primary example. With a lot of port offset and a little flow separation down there, if you sharpen those angles up, that port will go dead silent, especially through the transition, which is, the transition is the Venturi convergence point. That's where the curtain area and the throat are the same area. Everything changes at that point. And as soon as you hit about 550 lift, as soon as that curtain area opens up over the throat area, that's when she'll go turbulent, loud, nasty. That transition is always hard. So if you sharpen all those angles up, it'll walk right through that transition like nothing.
What do you see with you were talking about laying back the short side, and I look at the cross section. Just my brain and where it goes with that is, you're talking about NACA, and you've got the NACA airfoil look and everything. Do you study? I mean, do you see any correlation there? Of just when you're looking at a short term laying this back, of thinking about, you talked about using aviation, right? And would be my only point here of, like, is there anything you see in there?
They were completely unaware of that aspect back then. And we didn't understand it until we started shoving engine speeds higher and higher with 2-valve stuff. But yeah, that is still not, if you want specs, okay, lay it back this much and I can't give you that.
There's nothing there.
No, it's okay, well, the port is this high and I need this much airflow and yada, yada, yada. So I have to have this much area. So where am I going to put that relative to the deck and the valve? You got to play with it. Mm-hmm. Just got to play with it.
Is there anybody working on tabulating that? I mean, you've got.
I know it's between 50 and 70%.
Yeah.
of the valve.
Yeah. Yeah, I just think, it's so interesting to see in where technology
You can see it
goes.
in CFD.
Okay, yeah. And it's in CFD.
CFD gives you zero insight into the actual port shape.
Yeah.
It's that in that 3D environment, and maybe a lot of it's probably me, my perspective is skewed. I can't do a port in a computer and have it come out.
I think, and I went, like we were talking earlier, going to engineering school, and you kind of exposed to FEA, you get exposed to CFD. And I think there are some people who go down the path of that and probably do get very, very good at it and can, like you said, make the correlations.
The tools themselves in the hands of an experienced individual are deadly.
Yeah.
But the tools themselves won't allow you to do what he does.
Correct.
So using a port design tool without having the benefit of the experience, knowledge, or education is a worthless endeavor.
And that's what I would tend to agree. I mean, I think. Do you see any of that though? I mean, with the CFD software.
Oh, I see that a lot.
You do see a lot in the industry of people doing that.
Yeah.
And
the people, some of the guys who were doing the 3D manifolds were making all the mistakes we were making 30 years ago. And I saw it. I'm like, they'll get there, and they did.
Yeah.
Within 3 years, they got there.
How does it help? I mean, and I look at that. I mean,
the CFD won't tell you what the airfield distribution is. It won't tell you about runner isolation and separation. It won't tell you any of the stuff, the dynamics that actually go. So the first manifolds they came out with had a 2 airfield ratio splits front to back. The outside runners were all super, super lean because there was no runner isolation back there. There was no signal, and you couldn't get the airfield mixture over there. They leaned the walls in. Give it room. If you look at the SB2 NASCAR manifold, there you go. It's even. It's got this huge volume out here. It doesn't look aerodynamic or swoopy, but it's proper.
You talked, just in this kind of computer. I mean, you had some models up and cylinder heads and just talking cylinder head design, and I think about drawing those things even with the skills that I know, and I go, man, making a full model of a cylinder head and port design. I mean, that's
And you should.
a massive to do that though. It's you.
But
really
instead
have
of
to
making it, you should ship it to me or somebody else and say, hey, pointers. And
Yeah.
and there was a case where an individual wanted to do a certain engine, and he never designed a cylinder head before, and he designed some billet heads, and it was supposed to be the greatest thing in the world, and he had all this hope and drawn up in this, and he'd spent like almost $100,000, and the engine made 225 horsepower less because he did if he wanted to point to a cylinder that had absolutely everything wrong, it did. But it looked aerodynamic and swoopy and pretty and
looks can be deceiving.
Yeah.
You talked I guess with the EM69 HP, the key points there and Rottler stuff has always been digitizing, and that's the benefit is you can create, it creates a model for you then.
Not only that, it gives you latitude because you can hold the opening and the throat or apex and seat and increase and decrease your tooling offset. So if I do a port for a 200 valve, I have the latitude of a 250 or a 2180 or a 2150. I can just grow or shrink the port relative.
Yeah, and you touched on again. That was my question. I mean, I guess and I don't want to speak on your behalf in this, but if you're looking, you had a very nice slide on if I'm looking at designing, this is kind of what I'm going to look at. I like we said, I'm going to work around what's the engine designed to be used for, what's the design intent, and then what are the components that have been put into it, and that leads you to here, and then you go, okay, I've got my window to work within now. When you, I guess your approach on that design, how much of that are you using, do you use the Rottler system, the digitizing, you are, looking at that a lot first? Are you playing more with the 3D printed cores? I mean, where's your balance, I guess, would be?
The Rottler machines have a very specific use, and that's and there's a lot of latitude with them too. Mm-hmm. Let's say, for instance, we have, it is to take what I design and reproduce it, then it gives me the information. Then we look at it relative to water jacket, spring height. Let's say you had a spring that was too close to the top. Say I came in on the roof and it was too tall and I missed it and it's only 40 thousandths to the spring seat. Well, you can go in there and manipulate that and build that up right there, and you don't have to redo the port or fill it and redigitize it, or you can offset. You could do so much in there that would force another prototype to be made.
Another iteration, and just measuring. I mean,
another iteration.
I always say to them, how do you measure this shape, these port shapes? I mean, what do you? It's such a challenge.
There's so many different ways to do it. I mean, I've made so many devices. There's a guy in Australia that's got an expansion gauge now. You just put it in there and it'll tell you.
Oh, really?
It's got like 10 arms on it.
Huh.
But normally what I will do is use the machine. The old way was to actually measure it, kind of document your radiuses in the four corners because they're never the same. The radiuses on the roof are bigger than the radiuses on the floor, and then calculate it.
Talk to me a little bit about boosted engines.
Oh boy.
Yeah, that opened a can of worms, but
no, it's not a can of worms. It's just there's a lot of preconceived ideas out there that don't work. Like an alcohol engine, the old rule was, you got to go up 10 or 12%. Well, in some cases, yeah, that's right. In most cases, no, it's not. And if you have an alcohol carbureted engine, that port will be the exact same size as an NA engine because you're trying to move 2.4 times the liquid through that system. Okay, your inertia supercharging is going to go up. It's going to be harder to move, which is why an alcohol engine drops 400 to 600 RPM when you do that. Changes the harmonic, changes the density of the charge, it changes all that. But you can't pull fuel out of the carburetor without airspeed. The carburetor needs signal. So if you go to individual mechanical injection or EFI, then it gets bigger. See, so intended use dictates design. Mm-hmm. Turbo engines. This is a primary example of people think, well, if you're not turning the engine higher, you're just throwing more boost to it, and you throw another atmosphere at it, and the inlet temperature is the same, the port is the same size. Density. CFM is cubic feet per minute. That is not a density. That is not a mass flow measurement. if you double an atmosphere, you just have twice the molecules in that cubic foot going through the engine. Your airspeed's the same. And people have a hard time grasping that. Now, if you use a mass airflow calculation, yeah, you're going to see that, but the airspeed's going to be the same. Until you get to, you can't get there with an engine. Let's put it that way.
Yeah.
To where it's such a massive change that at the same inlet temperature, by the way. That's the caveat there.
Temperature, yes.
Yeah. Your inlet temperatures change. It can change things.
Well, we do have some members here in the audience. It's the cool thing about doing it in this format. And we'll open up questions to anyone. For Darin here, please feel free to ask. I will repeat the question for the filmed audience.
What about the new thing with the Burr finish?
So I'll just repeat that. The question is shiny manifolds and the Burr finish, just for those that are on film. Go ahead.
Again, the boundary layer condition, when you're trying to move fuel through something, like on an unlimited NA engine, when I have to increase the taper and lower the airspeed at the entrance to 220 feet per second, the air-fuel mixture falls out of suspension very easily, which is why we use that small radius. And upstream, I will use a 36 to a 40 grit finish in the runner. But as the airspeed increases, it will go to 60 and then 80. So the boundary layer condition is relative to the airspeed and the amount, and you want to jack it up off of there, okay, to get the fuel up off the wall, and it helps them much. So a Burr finish is something that uniformly, let's put it this way, if I had 36 grit all the way through the intake track, it wouldn't do anything negative. I do some of the stuff that I do to make it pretty because people want to see it. So a Burr finish is ugly and people don't like it for that reason, but it functions perfectly. You know, it's like CNC. It almost was a buzzword for a couple of decades. If they weren't CNC'd, they weren't good. At Profiler, we made cast cylinder heads. They moved the same air. They made the same power. They were $800 less. No one would buy them because they weren't CNC'd. A CNC is a Xerox copy machine.
They are.
You put a bad port in it, you get a bad port out.
Yeah, and I think, I always say that I like CNC because it lets you see, you put a number to things that you're doing, and then you can replicate it. It's a great way to put it. And but yeah, this industry for sure was a
it revolutionized the industry for me, especially. I could do 10 times the amount of prototype development, intake, exhaust port, combustion chamber, valves, Valvetrain, whatever, that I could do before.
And then you can make the same thing
10,000.
Well,
after
you spend your 10,000 hours, you can make it 10,000 times.
Yeah. And plus the latitude I have with them, push a button, grow it 10,000s, run it. It's like on the IRL project. I asked the engineers there, what's the gas speed? And I don't know. Okay. Well, what I did was I made tubes. We made tubes that slid down. They were individual ports on those things with a solid oval butterfly. And the injector split between the two runners. So I did an injector wet flow test and saw that one runner was taking more than the other, which was an issue. Fixed that, and then we didn't know what the gas speed should be, so I just made sliders that slid in there that changed them slightly, and then that would give us the trend.
Anyone else?
I never have.
Sandblasting of the ports.
Anytime you do A/B testing, which is, you have to do that. You can't learn anything. Anytime you make a small iteration, you have to either have a different set of heads that makes the same power and switch them back and forth and identify that, okay, this is a trend that's increasing this way. So let's go and exhaust that trend and see where it goes. But you have to do A/B back-to-back testing, otherwise you won't know. So if you've done that testing and you saw a power gain, the next thing I would do is I ask that hard question, why? Why in that port is it doing that? And there's no NA engine development programs now that allow me to answer that most of the time because it takes too much money and time.
I think there's just from my side, and I could be wrong, but with testing, especially when we look at dyno numbers, and what would be your opinion on that? Because, I mean, we're trying to understand here, like you said, A, B, A, B. We then put together this whole system.
If you're on the same, okay, repeatability is 10 times more important, or repeatability and consistency is 10 times more important than accuracy. If your dyno's 50 horsepower off, but it repeats every time, and you can see a small change in iteration and it will show it, I don't care. I can quantify the difference from dyno to dyno. How much difference do you think there is? And I've seen every dyno in the country, drag race dyno. I've had pro stock engines across almost every one of them. And how many actually have certified SEA weights to calibrate them? 1%. I'll tell you the painstaking efforts we went to at Ruhr Morrison. But how much power difference do you think there is? There's 80 to 100 horsepower between the worst to the most calibrated. But if that 80 horsepower down is consistent, that's fine. I can quantify that's an 80 horsepower difference, and I can relate it back to what I'm doing on this dyno. So at Ruhr Morrison, when you're trying to make 2.93 horsepower, when you're shooting for that 3 horsepower per cubic inch range on any NA engine, like I said, your tuning window goes to a point. So you're trying to find 1 horsepower here or there. That's 1/10 of 1% power. Now, how are you going to define and manage all the variables in that dyno cell? Because 1 degree of oil temperature could be 2 horsepower. 10 degrees of a cylinder head temp can be the other way. So what we did was we had an air conditioning system that's used in operating rooms. It's used to move the air through like 3 or 4 operating rooms. So what it does is it takes the ambient temperature, cools it down to 40 degrees, and wrings all the moisture out. Then heats it back up to 70 degrees and introduces in a 45-foot long tunnel this mist. It takes 25 minutes to stabilize. So any day, every day, it is 70 degrees, 50% humidity. Never moves. So the only thing that moves on that correction factor is that barometer. So our correction factor was 1.102 or 1.0006. It was almost nothing. So we minimized the atmospheric correction factor. Then you have to maintain, you have to know your cylinder head temperature, front and back, water in and out, oil temperature in and out. You have to know all the manifold pressures and everything, and then you set it up on your graph with this thin bar. My brother was the one that did all the engine building, and he had this thin green line, and all those variables had to fall into that green line before he walked into that handle. And if the engine temperature or head temperature, he'd shoot a little water in there, and sometimes it took 20 minutes to stabilize the engine to make a pull. But you can't see 1 horsepower difference unless you do that. You're guessing. That's why these $2 billion dyno rooms in NASCAR and all that stuff, that's why they're there. You can't tell a difference at that power level unless you stabilize all that stuff.
Anyone else? I guess the question there would be, does it apply to 2 and 4 valve?
Yes. Yes, it does. Of course, intended purpose dictates design. The port design that I would do, the runners that I would do, completely different. The signal from a 4-cylinder is massive, and their harmonics are really weird, and their vibration's horrible. So you have to take they would have lower mean gas speed, longer runners, less taper. They take a different approach. Just like a V12 or a V16 takes a completely different approach. So it's like tuning a trumpet. Do you have 8 trumpeters or 4 trumpeters, and you tune that harmonic, that sound. People who are good at tuning instruments could tune an intake manifold.
Well, we'll wrap up here. 2 questions for you, Darin, to close this one out. You mentioned about learning, and you're doing this. You've got this channel that's created. Where should people be going if they want to learn more, if they want to learn more?
Drag Boss Garage.
Drag Boss Garage. And we'll
DMI, Darin Morgan Induction. And what I've done is I've taken the whole AIST course and just broke it down. And before, what I would do is I would fly somewhere and spend 2 days, 20 hours, 10 hours a day, sitting here going through every single aspect of the design of the induction exhaust chambers, all that. But that's not enough time. That's just not enough time. So now with the channel, I can take each one of those individual topics and break them down into days and days and days.
And then to close it out here, in terms of the industry as a whole, everything you've seen, where do you think this thing is, what's on the cutting edge here? What are you seeing moving forward that you think might be something that you're honing in on, or that you're thinking the next generation maybe?
I mean, it's all going billet manifolds, designed in CAD, push a button, come back tomorrow, bolt it together, put it on the dyno. I mean, that's where it's gone. It's where it is right now. We're going to start 3D printing the actual parts within 10 years. I know that for a fact. I mean, whatever you want, you just grow it out of aluminum or whatever. I mean, we were doing that in SLA decades ago, you know, growing them in a vat out of plastic, put them on the motor and yanking it, see what happened. That was really cheap, but it takes, you know, days and days to grow that thing. And then they had faster machines, and I'll never forget, my brother ordered this gasket, and he had drew it out on a piece of paper, you know, and his specs, he didn't put the specs, but he drew the changes, and the gasket came back, and it was that big, actual size. Made out of copper. It was a beautiful little thing.
Well, thanks for joining us. Really appreciate it. This is wonderful, and there's so much more to learn. For everyone out there, engineperformanceexpo.com. Stay tuned for more, and we'll hopefully have Darin back again.